Okay, thank you. Good afternoon. My name is Mingfei. This work was done by me, my collaborator Zhenjie Zhao, and my supervisor Xiaojuan. We are all from the HCI initiative in HKUST. We all know that computer devices have become a part of our life. We are all surrounded by mobile phones, laptops, and tablets. And studies have shown that these computing devices have different influences on our face-to-face interpersonal interactions. They can be distractors, like we might be distracted by unexpected or irrelevant newsfeed or notifications for our mobile phones. We might also use our mobile phone to search some relevant information for our conversation, which means that the computing devices can facilitate the interactions between human beings. Due to the different influences, people have different reactions and mixed feelings towards the usage of computing devices. Since we are intelligent, we know how to cope with this situation and to mitigate the side effects caused by the computing devices. But what if the computing devices are used during the human-robot interaction? Computing devices can be regarded as social beings, and they can compete for the participants' attention. When people are using computing devices, their engagement status is ambiguous for the robot. If the robot fails to detect such engagement dynamics and fails to behave properly, chances are that the communication between the human and the robot is going to break down. So in this work, we consider computing devices in human-robot interaction. First, we try to detect the attention shift by using some low-level visual and auditory signals. On top of that, we introduce several engagement states and their transitions. By using these states and transitions, we try to infer the real engagement status and resolve some potential ambiguities posed by using the computing devices. Finally, we explore how the robot should behave during the whole process. We try to develop two strategies for the robot. This figure presents a framework of this project. Our work consists of three modules: a visual auditory processing module, the engagement inference module, and the behavior generative module. All these modules can be downloaded in this URL. First, let me talk about the visual auditory processing module. In this module, we extract some high-level social signals from some low-level visual and auditory signals. So by now, I haven't given the formal definition of engagement. So what is engagement? Engagement is a process with transitions from one state to another state. And engagement status can be indicated by some social signals like eye gaze, head pose, and body orientation, and so on. And most studies have shown that direct gaze is the most important to show the people's engagement status. Since it is not easy to measure the gaze directly, so we may use the head pose to estimate the people's gaze. So in our model, we also use the head pose to estimate the direct gaze. We denote the result as a binary indicator, the B gaze, with the 1 indicated the people is looking at the robot, and the 0 means that people shift their attention away from the robot to other computing devices. We also detect some other social signals like head nodding, head shaking, and voice feedback, etc. And denote all these social signals as another binary indicator. So these two binary indicators we are then fed into the second module, the engagement inference module. We also define our engagement states based on these two binary indicators as this, S1, S2, S3, and S4. So the pictures here demonstrate the basic idea of the definitions. Specifically, S1 is defined to be the scenario when people is looking at the robot without any attention shift. And S2 is defined to be the scenario when people shift their attention away but still provide some other social signals back to the robot. S3 is defined to be the scenario when people do not provide any social signals back to the robot, none gaze and none other social signals, but within a short period. S4 is defined to be defined to be the scenario when people do not provide any social signals back to the robot, but for a longer time. So after defining the engagement states, we then introduce the state transitions and all these conditions. Among all these states, 2 states are very important, S3 and S4. As I mentioned before, in S3, people do not provide any social signals back to the robot. Their engagement status actually is ambiguous to the robot. In S4, the people do not provide any social signals back to the robot for a longer time. So here I have to clear one more thing. The time interval here is determined by a previous study, which shows that people are very likely to be impatient when their partners are using computer devices for more than 6 seconds. So we set the time interval to be around 6 seconds. So on top of that, we also develop our behavior strategy on different states, which means that the robot behaves differently when it detects different states. And special attention has also been put on S3 and S4. So talking about the behavior strategy, let me introduce the last module of this framework, the behavior generation module. We adopted a similar idea from the human interaction and use the behaviors human conducted when their partners are using computer devices. First, we create a corpus, and then we annotated this corpus. From the annotations, we extract some special patterns from the annotations. Our corpus consists of 17 videos with different scenes, and then we annotated them from different angles. We put special attention to the gaze, head movement, and head movement. And all these annotations can be downloaded in this URL. Due to different personalities, we find that there are 2 styles of behaviors, different behaviors. We summarize these behaviors into 2 main categories, that is explicit strategy, implicit strategy. In explicit strategy, people behave in a more open and proactive manner. We then transplant some behaviors into the robot platform, and I can show you some demos.
Are you still with me? Are you listening?
The robot just speaks out the confusion. And the second demo.
Hey, you don't.
Oh, sorry.
Hey, you don't want to miss this information. I will repeat the last sentence.
So the robot raised his hand to regain the attention from the participants. For the implicit strategy, the people behaves in a more submissive manner. So we transplant some behaviors into the robot, like this. So the
Okay.
robot adds some conjunctions when the people are using the computing devices.
Okay, I will pause for a moment. Just your tasks.
So the robot will pause for a moment to wait for the attention come back. After implement all these modules, we then conduct a user study to evaluate our system from 2 perspectives. First, whether our system can effectively estimate the engagement dynamics. Second, how people feel about the robot behaviors. We propose our hypothesis from 3 aspects: the robot's communication ability, its role competency, and its perceived intelligence. The user study is set up in a dyadic conversation with robot as the personal assistant. And we set up one laptop as the peripheral computing devices. During the experiment, we randomly send questions to their laptop. Randomly set a question to their laptop. The questions might be relevant to the conversation or irrelevant to the conversation. It is all random. By doing this, we try to sidetrack the people's attention from the robot to the computing devices. Also, we adopted 3 strategies in the experiment: explicit, implicit, and unaware. Explicit and implicit are what I mentioned before. Unaware is the way robot does nothing special during the time when people are using computer devices. This strategy is used as a baseline. We also consider 3 scenarios. Some script samples can be found here. This user study is a within-subject experiment with 27 participants. All the experiment results are collected by questionnaires and post-study interviews. Here are some experimental results. So for assistant service quality, the robot with our strategies, either explicit strategy or explicit strategy, performs better in content delivery, conversation recovery, interaction smoothness, role competency, and desirability. For user experience, the robot with implicit strategy is perceived to be less annoyed, less controlled, less aggressive, more considerate, behave more appropriately and politely. So here are some insights from the experiment results. Pausing is always preferable. Since it can acknowledge the attention shift, also it shows that a robot is considerate and polite. Context-aware and intent-sensitive behaviors are also expected. How the robot behave should depend on the conversation content, and also it is supposed to respect the people's intent when they are using computing devices. Some other negative experience should be avoided, like the repetitive behaviors, like the robot should speak at different paces when people are using computing devices. So in the future, we are going to balance the turn-takings between the robot and the human beings. And we are also trying to consider some other elements like the active or passive engagement, like the personalities, either the robot personalities or the human partners' personalities. We are also going to consider more complicated scenarios and improve the robustness of our algorithms, try to overcome some face occlusion problem, to overcome some like head pose detection failures. So to sum it up, we consider computing devices in human-robot interaction. Actually, we propose a real-time engagement inference model for the robot. We also developed 2 strategies for a robot to handle dynamic engagement dynamics during the interaction with human beings. We also conducted a user study to show that some amazing or interesting finds. So that's my presentation. Thank you.
We've got plenty of time for questions. If you have a question, please just come up and use the mic in front.
Hi, my name is Nicole from UNO. Thank you, it was a really good presentation.
Thank you.
I'm very interested in if you looked at the voice of the robot, for example, if it was male or female, and where you would like to take the results of your study into a next future work.
Yeah, that could be possible. You know, we're trying to consider some personalities or other related elements into this scenario. So that's a good point.
Okay. Thank you.
Thank you.
So I have a question. Since you're using primarily subjective measures, if you had looked at, do you have any hypothesis about would you have seen any results in terms of how quickly people shifted attention back to the robot based on the different strategies? So more like if you were looking at objective measures?
No, we don't have such kind of measurement. Actually, we just measure how people can sense the detection. You know, we try to show the effectiveness of our system. Did you sense the robot speak something differently, like something like that? Yeah.
Let's thank Mingfei again.
Okay. Thank you.